For this project, our team decided to make a wind tunnel. Our wind tunnel is consisted of 3 different parts, which are contraction cone, chamber, and diffuser. The contraction cone is to pull a large volume of air to lower area to get a higher velocity in the chamber. This is a mesh in the front of the contraction cone to reduce the turbulence of the airflow, and a stack of shafts was set up between the contraction cone and the chamber to create laminar flow. And finally, the diffuser is there to help the air regain its static pressure. This wind tunnel was created based on two principles, which are conservation of mass and Bernoulli's principle, to create desirable velocity and pressure between sections. For example, the conservation of mass was applied for the flow between the contraction cone and the chamber since the area was decreased to increase the velocity of the flow, or the Bernoulli's equation was applied for the flow from the chamber to the diffuser because the air pressure in the chamber is lower than the pressure outside. That means the velocity in the chamber is faster. And considering the air is likely to flow from high pressure to low pressure, so the diffuser is there to make it easier for the air to get out of the chamber.
Using superposition of basic flows, we can represent the flow around a cylinder as a combination of uniform flow and a doublet. This gives us the stream function and the velocity potential. Using the stream function, we can see that at a distance r equals a from the center of the cylinder, the stream function will be equal to 0. So we're expecting to see a boundary layer on the surface of the sphere. Potential theory does not predict the separation of the flow from the surface of the cylinder, so in real life we're expecting to see a turbulent wake that occurs after the fluid passes over the cylinder, which is an example of potential flow just being an idealized model. This image shows the pressure field of the flow around the cylinder. The high pressure zones are shown in red and the low pressure zones are shown in blue. We can see that the maximum pressure on the cylinder occurs at theta equals 0 and theta equals pi. The velocity potential shows that the velocity of the fluid is equal to 0 at these angles. These are the stagnation points where the stream splits and flows around both sides of the cylinder.
After accidentally hotboxing our room, here are clips from our testing. In this first clip, we have the aforementioned cylinder. In this clip, we are able to see the turbulent wake that is created. The laminar flow appears to be ideal until reaching the turbulent wake point. In this next clip, we are able to see the flow around of an ellipse. The turbulent wake point appears, however, it is less dramatic than the previous example. Next, we will show 3 different angles. We have a shift in a counterclockwise direction. The length of our turbulence increases. The same occurs when increasing our angle, causing an increase in the length of our turbulence, until we reach a 90-degree angle, where a vortex appears at approximately theta equals 0.
Thank you for watching. We hope that you enjoyed it, especially the graders.
Keep pushing, keep pushing, keep pushing, keep pushing. Alright, that was a good amount.
Yeah, that was a lot.